This is section 3.4, and today we're talking about exponential and logarithmic equations. So let's go ahead and get started. Our first objective today is using like bases to solve exponentials. So if we look at this first example, we have 2 to the 3x minus 8 equals 16. Now, the nice thing about 16 is I can rewrite it as 2 to the 4th power. Now, I know that 2 to the 4th power and 2 to the 3x minus 8, if those are equal, then really their exponents here have to be equal as well. So I can now ignore those bases and just say, 3x minus 8 is going to have to equal 4. In order for those two to be equal, the exponents have to be the same. So if we add 8 to both sides, 3x equals 12, and divide by 3, we can see that x is going to have to equal 4. Now, if we look at our second example here, 27 to the x plus 3 equals 9 to the x minus 1. Now, in this case, again, I want to try to get these bases to be the same. And I know that I can rewrite both of those to have a base of 3. 27 is 3 to the 3rd power. But then that whole thing is being raised to the x plus 3. 9 is the same as 3 squared, but then that whole thing is being raised to the x minus 1. If we remember some of our exponent rules, when I have an exponent being raised to another exponent, I can multiply. So I can rewrite the left side as 3 to the 3x plus 9. And the right side is 3 to the 2x minus 2. Now notice that I distributed when I was multiplying there. You have to make sure that you distribute those exponents to both pieces. This looks a lot more like the previous question now. We have the same base 3. So I know if these are going to be equal, then that means that those exponents also have to be equal. So now we can ignore the 3's and we can say 3x plus 9 has to equal 2x minus 2. So we'll just solve for x. So x plus 9 equals negative 2. Subtract 9 from both sides. And in this case, x is negative 11. So by rewriting our equations to have the same base, we're able to then ignore those bases and just solve the equations. Now, if we look at the next slide, you can see that 4 to the x equals 15. That is not going to work in this example. I can't rewrite 4 and 15 to have the same base. So we need to use another method to solve these ones. That like bases isn't going to work here. Now the next method we can use would be to solve using logarithms. Just like when we're solving equations, when we can add things to both sides or subtract things from both sides, we can also log or ln both sides of the equation. Now you can pick either one, logging and lnning. It's doing the same thing. So in this first one, let's log both sides of our equation. So let's take the log of 4 to the x and the log of 15. So we went ahead and just logged both sides of this equation. Now, using some of the rules that we've learned in our previous sections, the nice thing about the exponents, using our power rule, is that they get to come down in the front of a logarithm. So I can now rewrite this as x times the log of 4 equals the log of 15. And now we can just go ahead and divide both sides by the log of 4. That gets the x alone. So x equals the log of 15 divided by the log of 4. Now this would be the exact answer. You could also punch this into your calculator and you could get the answer that way. I do want you to know that you can do the same thing with natural log. So you could have ln both sides. Let's just show it with the natural log. We could have done the ln of 4 to the x and the ln of 15 and brought the x down in front. And then divided by the ln of 4. Now, if you do the ln of 15 divided by the ln of 4, and you do the log of 15 divided by the log of 4 in your calculator, you will see that they actually are the same answer. So either of those would work. Let's look at our next example. Now, this one looks a lot more complicated, but it just requires a little bit of work first. The first thing I want you to notice is that we have more going on than just an exponential on the left side. So we need to get the left side down to only the exponential. My goal is to get this left side to only have that exponential equation. So we want it to only be this part right here, this e to the 0.6x. So we need to get rid of everything else. If I need to get rid of everything else, the first thing I'm going to do is add 3 to both sides. So when I do that, I get 40 e to the 0.6x equals 240. The next step to getting that e part by itself would be to divide both sides by 40. So now we have e to the 0.6x equals 6. 240 divided by 40 is 6. And now it's the point where I could log or ln both sides. Now, because this equation has an e in it, instead of using log, I'm going to use ln. So we're going to go ahead and ln both sides of this equation. So we're going to have ln of e to the 0.6x equals ln of 6. Now hopefully you can see that the reason I used the ln in this case is so that the ln of e cancels out to be 1. And really we get to take that 0.6x and swing it in front, and the ln of e is just 1. So it goes away. So now I have 0.6x equals the ln of 6, and I just have to divide both sides by 0.6. When you do that in your calculator, you will get approximately 2.99 for your x value. So the big idea here is that if your exponential is it has e in it, if it's an e, you definitely want to use the ln. Otherwise, you can use either ln or log. Now our next example looks a lot more complicated, but we're going to use a little bit of u substitution to see how we can turn this into a really easy question. In place of all those e to the x's, let's call those u instead. So let's let u equal e to the x. So when I do that over here in this first part, we're going to have u squared. We have this squared because we still have that 2 there. Minus 4u plus 3 equals 0. Now this is a nice basic quadratic that we can go ahead and factor. We're looking for two things that multiply to 3 but add to negative 4. So they'd be minus 1 and minus 3. And so when we use our zero product property, we can see that u would be 1 and 3. Only we didn't want to know what u equaled, we wanted to know what e equaled. Or I'm sorry, what x equaled. So if we do a little bit of substituting back now, we can say that e to the x, that's what our u was, has to equal 1, and e to the x has to equal 3. And now we just have two equations there to solve. In both of these, we'll start with e to the x equals 1. We're going to ln both sides. Notice I'm using ln because it's an e. And we know that in this case, the ln of e is just 1, so now we have an x alone. In the ln of 1, our properties tell us that always equals 0. So one solution to our equation is that x equals 0. If we do the same thing with the other equation, we'll bring that x down in front again, and we know the ln of e is just 1, so x equals the ln of 3. So we have two solutions this time for x. One of them is 0, and the other one is 3. Let's move on. Before we go on to our next objective, I want you to pause your video and I want you to try this free response question, and you'll be putting this answer into our Google document. Once you're done, we can go on to the next slide. So now we're going to be using the definition of logarithms to solve some log equations. So now our equations are going to be in logarithm form, not exponential form. Now the definition of log, that just means switching from logs to exponentials. So the idea we learned in class is the log loop. So we have the log base 4 of x plus 3 equals 2. Let's go ahead and use the log loop and rewrite this as an exponential. So we're going to say 4 to the 2 equals x plus 3. We know that 4 squared is 16. And if we subtract 3 from both sides, we can see that 13 equals x. Now, the one thing we have to be careful about here is we have to make sure that when we get our solutions that we don't have a time where we would have to take the log of a negative number. So we want to make sure to check our answers to make sure we're not taking the log of any negatives. So let's go ahead and check this solution right now really quick before we go on to the next question. If I put a 13 in for x, I'd have log base 4 of 13 plus 3. So I'd have log base 4 of 16. And 4 to the what equals 16? The answer is 2. So it looks like we're okay. Our solution does work. Let's go ahead and take a look at another one. Now in this case, I can't do the log loop yet. And the reason is because I have this 3 in the front. I want to be just left with my logarithm before I go ahead and switch it to an exponential. So we'll go ahead and start by dividing both sides by 3. If I do that, I have the ln of 2x equals 4. Now, when you go ahead and do the log loop, remember ln is log base e, so it's going to be e to the 4 equals 2x. To get this alone, we would just divide both sides by 2, and now's the time where you're going to grab your calculator and you're going to punch in e to the 4 divided by 2. Or you could just leave your answer in exact form. That would be the exact answer. Now, if we want to check this, let's go ahead and check our answer. We'd have 3 times the ln of 2 times e to the 4 divided by 2. Now inside the parentheses here, those 2's are going to cancel out, so we're going to have 3 times the ln of e to the 4th. And if you go ahead and punch that into your calculator, or we know that the ln of e is 1, and we can bring the 4 down in front, so we'd have 4 times 3, which is 12, and we can see that it does work. And remember, that's because the ln of e is just a 1. Okay? And so you can see in this case, both of these work. Let's take a look at another example. Now in this example, we have two different pieces here, two different log base 2's being added together. So we cannot do the log loop yet, but we can use the fact that they're being added to rewrite this with our product rule. So the first thing we're going to do is rewrite this as the log base 2 of x times x minus 7. And again, that's just rewriting it with our product rule. Now we'll go ahead and do that log loop. So we'll say 2 to the third equals x times x minus 7. And I'm going to go ahead and distribute and say x squared minus 7x. Two to the third is 8. And so if we get everything to one side so we can solve this quadratic, we'll subtract an 8 from both sides. We now have a nice quadratic that we can try to factor or do the quadratic formula. Two things that multiply to negative 8 but add to negative 7 would be positive 8 and negative 1. And we get two solutions here for x, negative 8 and positive 1. Now, don't forget that we want to make sure to check our answers. So let's start by checking the x equals negative 8. And it looks like if we go back for a second, we do have an error in our factoring here. Our factoring, I hope you caught it, should have been minus 8 and plus 1. So that's going to change our solutions to be positive 8 and negative 1. Okay, so now let's go back and start checking our answers. If we start with x equals 8, let's start checking that one, the positive 8 solution. We're going to have the log base 2, and we'll put it into the beginning, the log base 2 of 8 plus the log base 2 of 8 minus 7, which is 1. Now, 2 to the what equals 8? The answer there is 3. And remember, the log of 1 is always 0, so this equals 3. And so it looks like it works okay. We'll do the same thing for our other solution, negative 1. If I start plugging it in for my x's, I get log base 2 of negative 1. And I'm going to stop right there. I'm not even going to continue. The reason is that right now we have to take the log of a negative number. Remember that that is not possible. We cannot do that. We can't take the log of a negative, which means that x equals negative 1 cannot be a solution. So we have to take it out of our answers. So we're going to take out x equals negative 1, and that means our only answer in this case is x equals 8. This example shows you why it's very important that you go back and you check to make sure that your solutions work. I'm going to go ahead and give you an example to try, a multiple choice question, and then this is where we'll end this video for today. So go ahead and give this one a try, and we'll finish up this section tomorrow in class.